Imagine a future where massive space habitats, sprawling solar arrays, and powerful antenna networks are not launched from Earth in one piece, but are instead constructed piece by piece, high above our planet's atmosphere. A future where robots, equipped with advanced algorithms and innovative materials, autonomously assemble structures that could support humans on the Moon, Mars, and beyond. This vision is rapidly coming to life thanks to NASA's latest investments in autonomous assembly and in-space manufacturing technologies, developments that are reshaping the very foundation of space exploration. In August 2025, NASA took a bold step forward by funding groundbreaking projects aimed at revolutionizing the way large structures are built and maintained in orbit. One such project is the Automated Reconfigurable Mission Adaptive Digital Assembly Systems, or ARMADAs, a NASA initiative focused on developing the software and hardware necessary for autonomous construction in space. This project is more than a collection of research papers. It's a tangible leap toward building the future of human presence beyond Earth. At the heart of ARMADAs are builder robots, machines designed to assemble modular units called voxels. Voxels, much like the building blocks of a digital 3D model, are the foundation of this new era of space construction. The robots, equipped with specialized algorithms, can plan their movements and construction sequences, allowing them to autonomously create complex structures. Unlike traditional approaches that rely on massive positioning or measurement systems, these robots can operate with a high degree of flexibility, adapting to the unpredictable environment of space. The result is a system capable of constructing habitats, antenna arrays, and other vital infrastructure without direct human intervention. But why is this technology so critical? Traditional space missions have relied on launching pre-built structures from Earth, a method that is both expensive and limited by the constraints of rocket size and payload capacity. By enabling autonomous assembly, NASA can send compact, modular components into orbit and let robots do the heavy lifting. This not only reduces costs, but also opens the door to building structures much larger and more complex than anything previously possible. The ARMADAs project is more than a theoretical exercise. NASA has already demonstrated builder robots assembling voxels into intricate patterns, showcasing the potential for real-world application. With each test, the robots become more capable, learning how to handle the challenges of zero gravity, temperature fluctuations, and the harsh conditions of space. These advancements are paving the way for future missions where entire habitats or scientific equipment are built in orbit, tailored to the unique needs of each mission. Yet, autonomous assembly is only part of the equation. The materials used to construct these structures are equally important, especially when considering the challenges of repair and maintenance in the unforgiving environment of space. Recognizing this, NASA recently awarded a collaborative grant to researchers at Louisiana State University, Louisiana Tech University, and Southern University. Their project, titled Advancing Manufacturing of Sustainable Multi-Material Composite Structures for Space Applications via Ultrasonic Welding, is focused on creating lighter, stronger, and more easily repairable materials for spacecraft, lunar habitats, and space stations. The key innovation here is ultrasonic welding, a technique that allows different materials to be joined without traditional fasteners. This method offers several advantages. It reduces weight, enhances structural integrity, and simplifies repairs. Crucial benefits when working in space, where every kilogram counts and maintenance opportunities are limited. By combining materials with ultrasonic welding, engineers can create composite structures that are both robust and adaptable, meeting the evolving needs of space missions. This initiative reflects a broader shift in NASA's strategy, prioritizing in-space manufacturing and autonomous assembly as essential components of future exploration. By investing in these technologies, NASA is laying the groundwork for a new generation of missions that will not be constrained by the limitations of Earth-based manufacturing. Instead, astronauts and robots will build, adapt, and repair their habitats and equipment on the fly, responding to the dynamic challenges of life beyond our planet. The implications of these advancements are profound. Consider the construction of a lunar habitat. Instead of launching a fully assembled module from Earth, NASA could send a shipment of modular components and builder robots. Once on the lunar surface, the robots would autonomously assemble the habitat, using composite materials joined by ultrasonic welding for maximum strength and flexibility. Should a component be damaged by a meteorite or the harsh lunar environment, the same robots could carry out repairs, ensuring the habitat remains safe and functional for its occupants. Similarly, large-scale scientific infrastructure, such as telescope arrays or solar power stations, could be constructed and maintained in orbit. Autonomous builder robots would assemble these structures from modular voxels, using algorithms to optimize their design and placement. If a section of the array requires repair or upgrade, the robots could disassemble and reconfigure the modules, maintaining peak performance without the need for costly and risky human intervention. The ability to autonomously assemble and maintain large structures in space also has significant implications for missions to Mars and beyond. Long-duration missions will require habitats and equipment that can adapt to changing conditions, withstand harsh environments, and be repaired or upgraded as needed. NASA's investment in autonomous assembly systems and advanced materials is a direct response to these challenges, ensuring that future explorers have the tools they need to thrive on distant worlds. Moreover, these technologies are not limited to government-led missions. As commercial spaceflight continues to expand, the ability to build and maintain infrastructure in orbit will become increasingly important. Companies seeking to develop space hotels, manufacturing facilities, or mining operations will rely on autonomous assembly and in-space manufacturing to create the necessary support structures. NASA's early investment in these technologies is helping to establish the standards and capabilities that will underpin the future space economy. The development of autonomous builder robots and advanced composite materials represents a convergence of several cutting-edge fields: robotics, artificial intelligence, materials science, and aerospace engineering. The challenge is immense. Robots must operate with precision in a zero-gravity environment, materials must withstand extreme temperatures and radiation, and assembly processes must be both efficient and adaptable. Yet the progress made by the Armadas project and the ultrasonic welding initiative demonstrates that these challenges are being met head-on. As NASA continues to refine these technologies, the vision of large, autonomously assembled structures in space moves from science fiction to reality. The agency's commitment to innovation is evident in its support for collaborative research, its willingness to fund experimental projects, and its focus on real-world applications. With each new breakthrough, the possibilities for space exploration expand. Larger habitats, more powerful scientific instruments, and the potential for truly sustainable human presence beyond Earth. Looking ahead, the benefits of autonomous assembly and in-space manufacturing will extend far beyond the immediate needs of NASA's missions. These technologies will enable new forms of space architecture, from modular research stations to expandable habitats that grow as mission requirements change. They will support the development of space-based infrastructure, such as communications networks and power grids, essential for long-term exploration and settlement. And they will provide the tools needed to respond to unexpected challenges, ensuring that astronauts and equipment can adapt and survive in even the most hostile environments. The journey toward assembling large structures in space is just beginning, but the progress made in recent years is nothing short of remarkable. NASA's investment in builder robots, modular voxels, and innovative materials is laying the foundation for a new era of exploration. An era where the boundaries of what is possible are defined not by the size of a rocket, but by the ingenuity of engineers, scientists, and robots working together in the final frontier. In summary, NASA's recent funding of autonomous assembly and advanced materials projects is more than a technological milestone. It's a strategic commitment to the future of space exploration. By enabling the construction and maintenance of large structures in orbit, on the Moon, and eventually on Mars, these innovations are making it possible to imagine and achieve a future where humans live, work, and thrive beyond Earth. With each new discovery, the dream of building a sustainable presence in space comes closer to reality, driven by the relentless pursuit of knowledge and the spirit of exploration that defines NASA's mission. As we look to the stars, the next generation of space structures will be assembled not in Earth's factories, but in the vast expanse of space itself. Robots, algorithms, and advanced materials will work in concert, creating habitats, research stations, and infrastructure that will support humanity's greatest adventures. Thanks to NASA's vision and investment, the assembly of large structures in space is no longer a distant possibility. It's the foundation on which the future is being built.